So welcome to Math 317. This is the last lecture, lecture 38, and we'll be hearing about cryptography. Okay.
Okay, so I'm also doing my presentation about cryptography, but instead of like ECC and cryptocurrency stuff, I'm mostly going to be focusing on other asymmetric algorithms and just deriving most of the algorithms and formulas for those. So cryptography comes from the Greek meanings of the words crypto, hidden, and graphy, which is writing, and it kind of encompasses two things, encryption and decryption, or concealing a message and then unlocking it or revealing it. And it was first used in ancient Egypt, although it's most commonly known with Greece, like we talked about in class, with like writing messages on your slaves' heads and having the hair grow back. But Egypt, they put hieroglyphics on the walls of tombs, and most people actually don't think of these as a way of concealing secret information, but actually there was this sort of ledger that was passed down through the hierarchy that would decipher those. So hieroglyphics were a really early form of concealing a message that you needed only certain instructions to understand. And so today, cryptography kind of does something similar, but instead of passing something down that's physical, it makes use of algorithms for scrambling this data, and then similar ones for unscrambling it. And we can also use these to verify the data integrity, which wasn't something that was used back then. Awesome. And just Enigma, we'll talk about this at the very end, but it's probably the most well-known example of cryptography being used in history, specifically wartime. And so I tried to mimic it in code, but that's for later. Okay. Goals of cryptography and just how we'll be evaluating algorithms are confidentiality. You don't want to know the data. You want to protect it from unauthorized users, and you only want your sender and your recipient to be able to know what's in your file. So we'll have like three main roles, like sender, recipient, usually Alice and Bob, excuse me, and then attacker. So we'll call that C or E, so Charlie or Eve. Integrity, you obviously want to ensure that your data is in its original and unaltered form, like C or E hasn't been able to open your file and change it in transit. And authentication, you want to confirm that Alice is actually the one sending, so that goes into code signing and just assigning your name, sort of your digital signature, to a little package at the end of your metadata that's within your file. And non-repudiation, which is to assure that a message sender cannot deny sending a message. Great. So two things to talk about with cryptography are two-way encryption and one-way hashing, which is like how I like to think of it, because encryption is obviously reversible. You have encryption and decryption, where you convert your plain text to your ciphertext, and then vice versa. And it protects the data at rest, like when it's stored or archived, in transit, when it's in network, and in use, which is when it's in the data part of calculations. And this entire process is known as end-to-end encryption. While hashing is actually a one-way function that's super useful for indicating that the message has integrity, like we talked about before, and it takes an input and will produce a unique message output. That's called a digest. And this is super useful, especially in code, like in Java, when you have things like linked lists. But the plain text will get transformed by the hash function to kind of map to a unique output of a fixed bit length. So you'll have a string like ABCD, and it'll map to like something like 00 or 10 or something like that. And this acts as a digital fingerprint. It's one way, because there's really no way to take this code, like again, 10, and say, oh, I know that was ABCD. It's really just a way to identify your string, your message, anything you want to send. Great. So two things for encryption that we need to talk about first are the cipher and the key. Now, the cipher is really important because it's the mathematical algorithm that's actually used to perform the encryption and decryption. And they can be symmetric or asymmetric, which means that they use one or two keys respectively. And the key is the essential piece of information used to perform the mathematical function. So it most commonly can be a number. And it's used to alter data so that it's scrambled, and anyone without the key can't decode the information. And interestingly, encryption strength actually comes from the key, not the cipher. And the algorithms are actually public and often undergo public review. Thus, they're not secure. The key should be really secure. And so an example is ROT10, or the Caesar cipher, like we talked about in class, where you just rotate the letters of the alphabet by the certain digits. And so in this case, the key would be 10, the cipher is ROT, or the Caesar cipher. And this is trivial, a trivial kind of cipher to use, but back in Caesar's day, it probably wasn't, because they were still working with Roman numerals, and they would have to calculate 25 possible options before getting to the answer in the worst case. All right, so first, symmetric cryptography, where one key is used to encrypt and decrypt. And so this is similar to like one house key being used to open and shut all your doors, or one Wi-Fi password being given out to everyone. You really don't have confidentiality with who has the key, because there's just one and you can't assign responsibility to a specific owner. So a simplified example would be if Alice wants to send Bob a file, she encrypts it using the key, sends it to Bob. Bob would decrypt, same key, view it, edit it, do whatever, encrypt, same key, send it back to Alice. So obviously not very secure. There's a really big problem where if you have the key, you can do whatever you want. Some examples of this way of cryptography is actually used, although it might not seem like it because it is very risky, but you have things like DES, 3DS, and DES is a data encryption algorithm that uses a small key size. So that's 112 or 168 bits, not very secure. 3DS, I remember this because it's like 3 times slower, where you apply the same cipher to the block, each block of data 3 times. Blowfish, Twofish are pretty old. AES is actually still pretty used. It's the advanced encryption standard, and it's secure just because it has a 256-bit key. Although we'll talk about later, like most software companies and like developers who are creating their own data packages are moving towards ECC. Okay, asymmetric cryptography. This is known as public key, where symmetric was known as private key. And this is where one key is used to encrypt and the other key is used to decrypt. So the ciphertext is public, but only the recipient can decrypt using the private key. And it basically offers everything that we were talking about before, like confidentiality, non-repudiation, everything like that. So the way this will work, really simple, is that Alice and Bob will each have respective public and private keys. And so because the word public implies that they both know each other's public key. So Alice is going to encrypt her file using Bob's public key, because it's only meant for him, send it to him, and he'll be able to decrypt that using his private key. Then if he wants to do whatever, send it back, he'll encrypt using Alice's public key, send it to her, and she can decrypt using her private key. And so this is really important because it kind of gets rid of that protection problem we were talking before, where anyone can decrypt with the key because they each keep their private keys secret and only the public key is known, but that was used to encrypt. And so that's not really of use to anyone who's listening in. All right, so it kind of sounds like you would never want to use symmetric cryptography, but it's actually on the scale of 100 to 1,000 times faster than asymmetric, which can be a payoff that some people are willing to make to take that risk. A hybrid approach that I think might be really interesting would be to distribute private keys securely using asymmetric cryptography and then decode the message using symmetric cryptography. So you would kind of solve that key distribution problem we talked about, but you would also like reduce the time it takes. Great, okay. Hashing. So 2 elements of cryptography that use hashing to confirm user identity are digital fingerprints or signatures, kind of same thing, and the just general process of code signing. And so the way digital signatures work is, like I said before, you can have these outputs like ABCD, whatever, that map to a hash code, so 00. But then what if a string like hello also maps to 00? Like your hash function isn't specific enough. And this will happen all the time, like especially when you're working with programming languages. And so you need to find a way around this. Because this can be dangerous in the context of cryptography, because if you don't have a digital signature, you can have like a scam email or something that looks the exact same as the other email, and you have no way of knowing if that's valid, because it might have the same hash code, or like in this metaphor, it might look the same. And so digital signatures prevent this. And so the actual process of code signing is where it's not enough to just like sign your name at the bottom of a file, because anyone could put, an attacker could put any file in front of you and just say, oh, sign it. you don't really know what's on the file. They can change it, and you don't know if they can change it. So if you sign it, it looks like you did it, or you meant to sign whatever is above it. So hashes within a data structure called a code directory are going to seal the executable pages, files, and just all the metadata of your code. And it's that data structure that's actually signed. So you need to sign actually this little package that's called a code directory. Great. And just these signatures are awesome for providing assurance that software code has not been modified after it was submitted by the developer. Okay, awesome. So asymmetric encryption allows for the use of digital signatures to provide this kind of protection. And so if we do an example really quickly, because sometimes this is hard to understand with the public and private keys and just like how they come into play. So if we have Alice and Bob, and Alice has public key KA.
Just on a blank piece of paper, what do you want to do on the board?
Is on the board like okay for everyone? Is that okay? Thank you. Okay. And private keys, like it's secret. That's SA. Now she wants to send a message M to Bob, who has the same public respective KB, secret or private key SB. All right. She's going to encrypt her message first, like we talked about before, and call that KB. So with asymmetric cryptography, you're encrypting with the recipient's public key. Now she's going to use a hash function that's known by both, like ABCD to 00, to calculate her hash digest for this message. And we're going to call that H of M. She encrypts the hash digest using her private key, S of A. So she applies S of A to H of M, and this is encrypted. And Bob is going to receive all this information. So just these two things are going to go to him. Great. So now Bob, his goals are obviously to decrypt the message, but also to confirm Alice's identity. So first, he's going to want to decrypt. Apply his private key to A. And this is going to yield your original message. So now he has it, but how does he know that Alice sent it? He has to do something with her digital signature to make sure it was her. Usefully, he knows Alice's public key. So he's going to unlock this because her private key in this context was used to seal. And he's going to get H of M. Okay. But because we have this hash function that we've known before, he can calculate M and get an HM new. Create his own like code because we both know this hash function like ABCD to 00. And now all that remains is a check for equality. So if H of M, this value he unlocked, is equal to the value he calculated, he knows that Alice sent it. So just assume that's true. And we're good. Okay. And just when I first read about this, I like had a big concern with the like flip key role here because anyone can unlock H of M if like C or E is attacking this exchange. But H of M really isn't useful to anyone. Like if I were trying to hack this, intercourse, then I would just get 00 and I wouldn't be able to do anything else. So that problem's kind of solved if you notice that.
What you could do is if you wanted to pretend to be Alice, you could try to create some possible messages and see if it gives the correct hash value.
Right.
Because it's so unlikely that two different messages will have the same hash value. You can be very hard pressed to guess this.
Yeah. And hopefully your hash function is a little more complicated, but great. Okay, now, whoa, no, not that. All right, this one first, because this one is my favorite, and then RSA is my least favorite. So we're gonna do that next, back to back. But DiffieHellman is kind of this hybrid method that I talked about before, where you securely exchange cryptographic keys over any public communications channel. And so we talked about this a little bit yesterday, like it can be the most unsecure network ever. Like you can be using like some random guy's VPN that he like put on his GitHub or something, and it won't matter because it relies on jointly derived keys or secrets that you'll use to encrypt and decrypt. Okay, so if Alice and Bob now want to talk about something else, first they have to agree on some prime P and a generator or base G. And the only restriction for this is, well, obviously prime, and then G just has to be smaller in some way. Great. And so again, they're like screaming this over some random guy's VPN, super insecure. It doesn't really matter. Whew. Alice. And so Alice is going to choose a secret integer A, and this is her private key. So private key A, and this is an integer. And Bob, respectively, private key B, also an integer. Now, they're going to use these numbers to perform a calculation and get another number that they're going to exchange again over the insecure network. So they're doing this, on their own. They're not talking to each other right now. So Alice is going to find G of A mod P, taking that to this prime, and Bob's going to find G of B mod P, mod P. All right, that is their public key. So, and this gets exchanged. So they both know this information, G and P, and then they switch these what yields at these functions. And so now Alice can generate, she receives Bob's public key, and she can take this whole thing to the A. So that's really only going to affect, what's in front of our mod. So G of B is the A, and then, you know that that's GBA mod P. Bob can do the same thing. Take what he received from Alice, GA mod P, whole thing to the B, and then that yields GAB mod P. And then you really wouldn't expect it to rely on something as trivial as this, but it's just that these are even. And so then now they have this shared secret number. And yeah. They don't know what AB are because of the mod. But well, they know their own AB.
They know their own A and B, but they don't know the common value. They don't know the product. They don't know what power G they have.
Right.
They just know that we both have the same power.
Exactly. And so an attacker is going to know PG, Alice's public key, this, and Bob's public key. And you're unable to calculate the shared secret from those values because, again, you only need your own singular number to raise it.
Yeah, we don't know a way to calculate.
Okay, yes. Some guy who's not going to share it with anyone knows a way to calculate it, but we don't yet. Okay. Asymmetric algorithms, RSA, another one. This one's fine. It's pretty secure. And you can use, when you're like modeling this yourself, you use a lot of like tools that we learned about in class, like fast multiplication, Fermat's little theorem, and the Euclidean algorithm. For the numbers that I'm going to choose, like my example, I'm only going to use the Euclidean algorithm, but fast multiplication, obviously for multiplying, and then Fermat's theorem is for picking your primes for them to be large enough. But we're going to use 11 and 5, so we don't really, not going to do that. Okay, so first step, select two, preferably large, but I'm not going to, random primes P and Q. And you're going to calculate this thing called the RSA modulus by multiplying them. Oh, that's not cute. And you're going to call it N. That's 55. And then we're going to calculate the totient, which is P minus 1, Q minus 1. In this case, that's going to be 4 and 10. That's 40. Okay. Select a number E of your own choosing that's relatively prime to the totient and is smaller than it. So in this case, we have E can be 3, 7, 9, 11, 13, 17. And I'm going to choose 7 just because you don't really end up with like the same 5 and it doesn't get confusing. So we're going to say choose E. 7. Now, we're going to find the modular inverse of E with respect to the totient. And we're going to call this D. And so this is where the Euclidean algorithm comes in. Sorry, I should go to the next one. because you need to solve this equation. E, D, the product, mod totient, so mod 40 basically, equals 1. And this just means that you have a remainder of 1 when you divide these things. Okay, so now we're going to apply the Euclidean algorithm using your e-value and your totient value and your e-value for x and y. So that yields 40x plus 7y equals 1. And we're going to work with 40. 40, okay. And we're going to do this entire thing, breaking it up and then back substituting in. And I think we did an example like this in class, but we only did like the first 2 steps and we didn't finish the Euclidean algorithm. So that's why I'm just going to do this part really quickly, hopefully, and correctly, hopefully. 40 equals 5 times 7 plus 5. You get your 7 from here, drop it down. So 7 equals 1 times 5 plus 2. 5 equals 2 times 2 plus 1. Okay, awesome. Back substituting this in, because you're going to get another equation in the form of ax plus by equals 1. And you're going to be really interested in what's in front of your second variable, because your first is going to be 40, and that's going to yield your p-value. So back substitution, 1, taking that all the way from the right, from this last equation, 1 equals 5 minus 2, it's 2, 1 equals 5 minus 2. Looking up at our second to bottom equation, we can substitute 7 minus 1 times 5. Then 1 equals, simplifying this and grouping together the 5s, 5 minus 2 times 7. And we're really just looking to get to that top line because we want to see that 40 again, because we're going to be really interested in what the other number is. 1 equals 3 times 40 minus 5 times 7 minus 2 times 7. All right, distribute and group. 1 equals 3 times 40 minus 17 times 7. And then, like I said before, we really care about what's sitting in front of the 7 when we reach the bottom of our substitution. And so if this is a positive number, like if this were any positive number, that would just be our D value. But because it's a negative, we need to subtract. So D equals 40 from our totient minus 17 equals 23. And so now we have our private key and our public key. And in practice, these will be huge, but for us, they're just going to be private is 2355 and public is 755.
You mean private, you mean 40 in the previous line. 23 and 40 is private.
Oh, yes. Excuse me.
You're keeping the totient private. You're making public the product of 2 primes. So
Right.
55 is public. But you keep
Yes. Oh, and you keep I attach this to the totient.
Yes.
Okay, awesome. So this is pretty secure, although, I mean, it's tedious to do by hand, but it lends a lot of security. And so far, no one really knows how to solve this except for like the NSA, and then maybe some other guy too.
We don't know what they know.
Exactly. So we don't know what anyone else knows, but yeah. Anyway, okay. Elliptic curve cryptography. We talked about this last time, but I just think it's super interesting because this is what's used in your phone because it's really space efficient and you get a small key, but a really high level of security. So let me see how I'm gonna draw this. Let me erase this. So like we saw last class, the equation for this is going to be y squared equals x cubed plus ax plus b. So RSA does something similar with prime numbers instead of using elliptic curves, but elliptic curve cryptography is really powerful. And it's just based on the algebraic structure of elliptic curves over finite fields. And you're going to choose a smaller key size that'll lend the same amount of security as RSA at a more space efficient level. And based on the values given to your A and B in this equation, your curves are going to change shape, of course. Larger curves tend to lend more security. So in practice, these numbers would again be very large, but I'm not going to assign specific numbers because we're just going to use P, Q, and R and Z, and things like that. Oh, it's 2. Okay. So the general way this is drawn is kind of like this. Okay, that'll work. And we're going to start at a starting point P. And like we talked about yesterday, when you draw any line through this curve, it's going to intersect and at most 3 points. And so let's call this P and Q and R. And the notation we're going to use for this is that P dot Q yields R. Great. And like we said again yesterday, if we drop this line down from R to its negated Y value, we're going to get a new value. I'm going to call it T, but we proved that it's basically P plus Q. Now we're going to draw P over to this T value. And so P dot T, I'm going to call this U, is going to yield this value U. Great. And then bring it back up to its negated Y value again. And I'm going to dot it. We're going to call this value, what, Y, anything. And because I only want to do this one more time, we're going to finish here. And so this is going to be our ending value Z. And so your public key is actually going to be where you start, P, and the point that you end on, Z. And your private key, interestingly, is going to be the number of times you dot P to get to Z. P dot. All right. So if we're given a function that describes the curve, if we have this and we have these points, it's really hard to find out how many times we dotted P with itself to get to Z.
You're doing dotting, not adding.
Yes, I'm doing dotting. Adding would just like, again, be this process of dropping down. But yeah, I'm just going to call those new points. Great. And so this is super secure. Probably not something like this, but in practice, you're going to choose this really large prime number that's going to be your maximum M. And you take this entire equation, mod M. So the mod is always going to show up. And that's why it's so hard to solve, because you don't really know how many times you've looped over to get your answer. Great. So ECC is just used in Bitcoin because it's more space efficient. And this just shows the key size in bits you need to achieve the same level of security in ECC and RSA. And so I just thought this was cool. And I included the like 384 point because that's what's considered strong enough to encrypt top secret information in the US government. So yeah, interesting. All right, before we finish up, just some more general applications of cryptography, like what it's been used for in the past. All these things. I'm really interested in VPN. I think that's super cool. Like creating your own private network to publish information. Like would cryptography even need to be used if you can make your connection secure enough? That's something else. But obviously sending digital money and then Enigma, I also found super interesting because like all the ciphers and things that we talked about, like the Caesar cipher was secure in like 100 BC or whatever, because they were using Roman numerals. And so cryptography and the security of the cipher you're using is really dependent on the computational power available to you at your time. So like RSA is above the ability of most people. Like I wouldn't be able to do this with like probably a tiny bit bigger, more numbers, but.
So I wouldn't say the Caesar cipher was ever secure because
Right.
there's only, on the order of 25 possibilities to try.
Right.
The fact that people didn't know it was being encrypted like this, that would mean so few people could read back then, just writing something down was almost enough for security.
Right.
And the fact that it looked like gobbledygook as soon as somebody knows it's using some kind of CISA cipher, they can crack it very quickly.
Exactly. But they probably like couldn't make like a Python program to like
No, but
do
I'm
that
saying
in a
you
second.
only have to try 25 things, and you can
Right.
easily create lookup tables and just keep trying it. It's very easy to crack the CISA cipher.
Totally. And then maybe for some other guy, it's super easy to crack RSA. We don't know. But the point is that it's dependent kind of on the security of the system you're using is dependent on the computational power you're assuming that someone else has. And so I thought that I could kind of mimic Enigma to do that today, like in code. And so a ton of people have already done this. This isn't mine. This is from some person's GitHub. I think his name is like Dave. This is like a classic Java developer, but this is Java. And so that's object oriented. And so he reasoned that he would use Java because he wants to like model each specific part as its own object, which makes sense because Enigma like was a giant physical machine. And so it had 3 parts, which are 3 rotors, a reflector, and a plug board. And each of these parts somehow would permute the alphabet. And the plug board has 26 jacks, 1 for each letter, and 6 cables that would can be plugged in and swap pairs of letters. Each rotor was a disk with 26 inputs and 26 outputs. And again, you would have cables within them that would swap every pair of letters. So in the rotors, every letter was going to get exchanged. The reflector, once your input passes from rotor to rotor, the reflector would take the output of the last rotor and then swap the pairs of letters like a plug board, except this swap would be immutable. You can't really change it based on your settings for the machine. So here's just how here's how a single character would flow through the machine. And so after you finish, there have been 9 separate substitutions. And so when I saw this, I was confused about why you wouldn't just want to make new copies of your input each time. Like before in the program I showed before, he was kind of changing it after each step, which makes sense, but then that's really hard to debug. And then if you want to do something like try and break the machine, it's kind of trivial. And you can back it up kind of from the point, but kind of from a developing point, you can just reverse the program. And so this is my code. And I modeled this in F#, which is not object oriented, it's functional, which means that I have to not modify the original input, and instead I would make copies of the new variable. So I would maintain my input A while moving it through each of these parts and kind of creating, like move through rotor 1, okay, B is created, I keep A. Whereas in the previous implementation, A is kind of lost after you go through that. I really like F# also, just to like plug F# because you can use smaller functions. And so like at the top, that's like my abstract syntax tree. And so everything is defined from the get-go. And I can just pass my input through all of these again, creating a new copy. And it's super easy to keep track of, just like the beginning of your file. And those are errors because I extended the wrong thing. And then I already put in the slides, so whatever. So great, I don't know. Everything is just dependent on what you have available to you at your time. And so it would be interesting to see if you can crack Enigma written in like a ton of different languages. Like if I eventually develop this into like an API or like its own compiler, I think it would be cool to see how I could take the input and then come up with it. That's all. Thank you.
I've actually seen original Enigma machines.
Really?
Yes. And so it's fascinating what you can do. So much of the efforts to crack the Enigma were assisted by the fact that certain people, all of them Polish agents, were able to get copies of Enigmas out of Germany and then give that to the allies to look at. We had heard a little while ago about the security of the CISA cipher. Well, when there's only 25 possible shifts, 26 on that order, there's not that many things to try. So people try to come up with more interesting ones. One of them is, I'm probably going to spell it, the Vigneri cipher. And so what you do is you take your string and then you take a keyword. Somebody give me a good word.
Orange.
Orange. Probably should have changed the color. And you just keep writing the word orange underneath it. And then what you do is you just add as you go down. So A would be you shift by 1 unit. E would be you shift by 5 units. And so the advantage of this is the same letter can be encrypted different ways. If you have a key where you have, B, something, something B, this B is shifted by 1 and becomes a C. This B is shifted by 5, B, C, D, E, F becomes a G. So depending on what letter of the key phrase is underneath you, you get shifted by a different amount. So the longer your keyword, the harder this should be to crack. If you take maybe a phrase, it was the best of times, it was the worst of times, Dickens was paid by the word. If you take that as your key phrase, it's really hard to try to do various attacks on this. One thing people often do with a simple substitution text where each letter is sent to a fixed letter is you do a frequency analysis. What's the most common letter in English? E. What's the most common pairs of letters? If you had to guess.
T and H.
Probably T and H. And triples THE is going to be very high. So by doing frequency analyses, you can often make wonderful guesses as to what's going to go on and then crack simple alphabet ciphers without too much trouble. With something like this, different letters are now encrypted differently. So you would have to break it up into different bins. So if I happen to know that the keyword had length 6, I could break my message into 6 smaller messages and maybe just hope in each one of the 6, E is still the most common. Try games like that. The longer your key phrase is and the shorter your message, the harder this is going to be. It turns out, however, that there are tricks you can do to guess the key length. The other thing is the security of this was not as great as people thought, especially if you don't do things properly. And this is one of the best lessons. It doesn't matter how great your system is, if you have a fool using it, or if you have somebody who accidentally doesn't realize that there's a, how to phrase this diplomatically, that there's a vulnerability, that there's a backdoor that they're opening for people by mistake, your system could be a lot less secure. So one of my favorite examples is on the order of 10 years ago, they discovered an encrypted message from the Civil War that had never been delivered. It was found in a river outside Vicksburg. And it was encrypted using something like this. Now, of course, with modern computers, it's not hard to crack. But people were wondering, could you just crack this using paper and pencil? And several people were able to do so without any trouble. And the reason is they assumed some structure about the letter. Hey, maybe this letter was written to the general commanding Vicksburg. Let's guess, does it start with, dear general or general so-and-so? And when they did that, they actually found, without too much trouble, exactly what the message said. And the reason the message was never delivered was there was a message from a Confederate general saying, we're sorry, we have no more supplies or reinforcements to give you. You're on your own in defending Vicksburg. And when the courier arrived, he arrived, I think, on July 4th, just after the Union flag went up. So seeing that the city had fallen, there was no need to go in and deliver the message, so it was thrown in the river. But again, you've got to be very careful when you're doing any system that it's executed properly. And for Enigma in World War II, there were certain stations that began every day by broadcasting the weather report. And if you know they're broadcasting the weather report, this gives you a little hook to get into figuring what's going on. All right, so we've got a couple of minutes left. So much of cryptography is related to being able to do things efficiently. We saw the Euclidean algorithm runs in logarithmic time. So if you have numbers of size 10 to the 400, the number of steps you need is on the order of the log of that. Well, the log of that is on the order of 1,000. We can do 1,000 calculations. So just briefly, let's just go through what RSA is. So you have public, some number n, and an E for encrypt. And private, you have P, Q, and D, such that P times Q equals n, and E times D is congruent to 1 mod P minus 1, Q minus 1. And the way it works is you take a message M that's relatively prime to n. It's going to be extremely hard to choose a message that happens to have a common factor with n. N only has 2 non-trivial factors, P and Q. It's extremely unlikely with a 200-digit prime that your message happens to be one of that. And what you do is you send M to the E mod n, And then the recipient computes m to the e mod n to the d mod n, which by the glories of mod arithmetic is the same as m to the ed. And it turns out that that equals m mod n. So this is absolutely amazing. When you raise the message to the dth power and you look at the remainder, you get back the original message. We can do this quickly using fast multiplication, using repeated squaring. So even though E and D could be of size 10 to the 200, 10 to the 400, we can do this very quickly. The miracle is, why does m to the ed, why is that congruent to m mod n? So how many of you have taken a group theory class? My hand has to be down because I have not taken group theory. I've taught it, but have not taken it. There's a problem being a double major. So we have Fermat's little theorem, we use the lowercase l, that says if A and P are relatively prime, then A to the P minus 1 is congruent to 1 mod P. This is a special case of Lagrange's theorem. So if you know group theory and you know Lagrange's theorem, this is just a special case. What I'm going to do is I'm going to give a quick proof that's very elementary. And I'm going to generalize this ever so slightly for what we need for RSA. This is not the best way to prove it, but it allows me to show one of my favorite proof concepts. Start with something simple and see how much you can milk from it. You know, reduce whenever possible in life to something you've seen before. So this is a pre-core class. I know some of you have already started to take core math classes. I want to start introducing you to the more theoretical proofs you're going to start to see. All right, so since the GCD of A and P equals 1, we have some interesting facts. So consider 1, 2, dot, 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 P minus 1, and A, 2A, 3A, dot, 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 P minus 1A mod P. So we clearly have the same number of numbers on both sides. The numbers on the left, if you look at the mod P, they're just the numbers from 1 to P minus 1. What about the numbers on the right? When you look at the mod P, what can you say? How many distinct numbers do we have? What do you think? Do you think they're all distinct, or do you think there's a collision? Do you think two of them have the same remainder when you divide by P?
Yes.
So you think maybe 3A and maybe 17A are the same mod P? So it turns out they're all distinct. If, say, KA equals LA mod P, then when you subtract, you get K minus L times A is congruent to 0 mod P. That means K minus L times A is, some number, some integer number of P. P doesn't divide A, so P divides K minus L. So P does not divide A, so P divides K minus L, therefore K equals L. So these numbers are all distinct. All right, so since they're all distinct, 1 times 2 dot 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 times P minus 1 is the same as A times 2A times 3A dot 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 times P minus 1A mod P, because they're all just the numbers 1 to P minus 1 permuted. All right, well, the left-hand side is just P minus 1 factorial. What about the right-hand side? What does the right-hand side equal?
A times P minus 1 factorial.
Almost. I agree that there's an A. I agree there's a P minus 1 factorial. A to the power of P minus 1. We have A every single time. Mod P. So we get P minus 1 factorial times A to the P minus 1 minus 1 is congruent to 0 mod P. P doesn't divide, right? because all the numbers in the product from 1 to p minus 1, none of them is divisible by p. So a to the p minus 1 is congruent to 0 mod p. So a to the p minus 1 is 1 mod p. Okay. So consider 5 to the 6th power, I'm sorry, 5 to the 5th power mod 6. Can somebody tell me what 5 to the 5th is mod 6? Well, this is the same as 5 squared times 5 squared times 5 mod 6. What's 5 squared mod 6? 1. So this is the same as 5 mod 6. Does everyone agree that this is not 1 mod 6? But a to the p minus 1 is congruent to 1 mod p if p is prime and a and p are relatively prime. What can you conclude about 6? 6 is composite. We've just proven 6 is composite without giving a factor. So you can use Fermat's little theorem to often check to see if a number is prime. Sometimes you can determine that the number is composite without even knowing a factor. Other times it might pass this test. So you might then have to try another A, and maybe you can find a different A where it's going to fail. Unfortunately, there are infinitely many numbers that pass this test for all A, but are composite. These are called the Carmichael numbers. They're rare, but they do exist. So you can't use this to prove that a number is prime, but you can get a number is probably prime very quickly, and then you can use slower tests to make it provably prime. So again, we're really concerned with efficiencies in this class. By doing a quick test like Fermat, we can winnow our candidates for primes very quickly and then use the slower tests. So what we need is we need a to the p minus 1 times q minus 1 is congruent to 1 mod p minus 1 q minus 1, as then a to the p minus 1 q minus 1 times any power plus 1 would be congruent to a mod p minus 1 q minus 1. And remember, we have ED is congruent to 1 mod p minus 1 q minus 1. So that means ED is p minus 1 q minus 1 times some integer plus 1. So the message to the ED is the same as the message to the p minus 1 q minus 1 k plus 1, which would be the same as the message mod p minus 1 q minus 1. So if we can show that we can generalize Fermat's little theorem to a product of 2 primes. So instead of a to the p minus 1, we want a to the p minus 1 q minus 1 to be 1 mod p minus 1 q minus 1. That's going to be what we need to make RSA work. Then when we raise our message to the ED, we're going to just get the message back. So we've got about a minute and a half left. So here's the proof. We know a to a prime minus 1 is congruent to 1 mod the prime. Assume a is relatively prime to PQ. So a is relatively prime to P, and a is relatively prime to Q. Take a to be a to the p minus 1, and the prime to be P. And the prime to be Q. That's going to give us a to the p minus 1 to the Q is congruent to 1 mod Q. And now we apply Fermat's little theorem again, but now we do it to a to the q minus 1, and the prime is P, and that's going to give us a to the q minus 1. Oh, sorry, this should be to the q minus 1. To the p minus 1 is congruent to 1 mod P. So we have the same integer. So a to the p minus 1 q minus 1 is congruent to 1 mod P and 1 mod Q. So I'll leave it to you as an exercise to prove that the only thing that works is it's got to be congruent to 1 mod P and Q. We know that works. You just have to prove nothing else does. And this is a way to prove a slightly more general version of Fermat's little theorem by applying the easier version twice. This is not the best way to prove the generalization. This is not the best way to get to Lagrange, but it shows you how you can build up on what you already know. All right, so this is a good place to stop. And then I will